You know, for decades, our approach to space has been, well, kind of primitive when you really think about it. We launch something up, cross our fingers, it survives the incredibly violent journey, and when it eventually runs out of gas or breaks down, we just leave it there, alone in the dark, to die. But today, we're right in the middle of this massive shift. We are officially moving from an era of disposable space assets to a sustainable, serviceable orbital architecture. Welcome to The Explainer. Let's dive right in.
So the real problem here is that our traditional space paradigm treats these multi-million-dollar spacecraft as completely 100% disposable. If you look at databases like the Union of Concerned Scientists, you'll see a huge percentage of early satellite retirements aren't actually due to broken hardware or getting smashed by orbital debris. It's simply hydrazine depletion. They literally just run out of gas. We are throwing away billions of dollars in fully functional geostationary assets every single year. Because without station-keeping propellant to fight off the gravitational pulls of the sun and moon, an asset is totally useless. It is literally like abandoning a $500 million Ferrari on the side of the highway just because the gas tank is empty. Crazy, right?
So for today's explainer, we're going to cover 1. The disposable space architecture, 2. The economics of life extension, 3. Active satellite servicing programs, 4. Modular and self-healing spacecraft, and 5. The dual-use security dilemma. Okay, part 1. The disposable space architecture and early satellite death. Now, running out of fuel is bad, but the financial toll of orbital congestion is just staggering. Low Earth orbit suffers the vast majority of hypervelocity impact losses. We're talking anywhere from $79 to $102 million lost every single year, with over 70% of those collisions happening in that highly congested 600 to 900 kilometer band. Geostationary orbit, on the other hand, only sees about $1 million in losses. But in LEO, untracked, millimeter-sized debris can easily puncture a propellant line or just completely shatter a solar array. It's gotten so bad that operators have to allocate up to 10% of their total mission costs just for defensive design and tracking. Add in the fact that up to 60% of LEO satellites historically violated their end-of-life deorbit guidelines, and, well, we've basically created a massive, dangerous graveyard up there. But to combat these losses, an entirely new multi-billion-dollar servicing market is exploding. This market is valued at roughly $1.8 billion today, and it's projected to hit nearly $7.9 billion by 2034. Right now, it's heavily led by docking, which holds about 42% of the market. Then you've got refueling at roughly 36% and component replacement at 22%. So instead of launching a brand new satellite, operators are finally looking to these services to maximize what they've already put up there. Which brings us to Section 2. The economics of life extension. Let's actually run the numbers here, because the net present value break-even point is just a total no-brainer. Think about it. A state-of-the-art geocommunication satellite costs $300 to $500 million just to build, plus another $100 to $150 million to launch. Historically, we retired these after 15 years because they ran dry. But if you spend roughly $65 million to rent a mission extension vehicle, or MEV, for a 5-year extension, that easily outweighs the $500 million cost of replacing it. Even better, if your satellite has a refueling port built in, you can get 100 kilograms of hydrazine delivered right to you in orbit for about $20 million. And since that satellite continues to generate $20 to $30 million in transponder revenue every single year during its extension, yeah, the ROI is absolutely massive for both commercial and military operators. And this isn't just a trick for those massive GEO satellites either. For LEO mega constellations, think Starlink or Amazon Kuiper, on-orbit refueling slashes their per-satellite cost amortization by 40 to 50%. When you remember that a constellation refresh cycle costs between $5 and $15 billion, extending the life of those individual small sats by just a couple of years effectively multiplies their return on investment and pushes those incredibly expensive refresh cycles way down the road. Moving right along to Section 3, active satellite servicing programs. So who's actually doing this? Well, Northrop Grumman's MEV-1 and MEV-2 are already fully operational in GEO right now. They use soft docking mechanisms to literally take over the propulsion for dying assets. Then you have DARPA's RSGS, planned for 2026, which is going to use highly dexterous grappling arms to do upgrades and repairs. Over on the debris removal side, we've got ESA's ClearSpace 1 and Astroscale's ELSA series testing out in LEO. But, it's not all smooth sailing. Take NASA's OSAM-1. It was originally designed to use a robotic arm for complex xenon transfer to unprepared satellites, but it was unfortunately canceled after burning through over $1 billion. It just faced too many cost overruns, schedule delays, and frankly, the industry is shifting away from trying to service spacecraft that weren't built to be serviced in the first place.
And the engineering approaches to all of this are just wild to look at. You've got ESA's ClearSpace One, which literally uses a giant four-armed space claw designed to envelop, grapple, and safely deorbit dangerous space junk. And right alongside that, you have completely different architectures, like the Orbit Fab refueling shuttle, which is basically pioneering this gas stations in space model. These are the machines laying down the actual physical infrastructure for a fully automated orbital economy.
All right, Section 4, Modular and Self-Healing Spacecraft. Now this is where things get really forward-thinking. Orbit Fab's Rafty valve is an absolute game changer. It's essentially a $30,000 off-the-shelf gas cap for space. Operators just surface mount this little octagonal grapple fixture and valve core onto their spacecraft before launch. That's it. It allows any new satellite to safely dock and transfer fluids, which means you can make frequent orbit and altitude changes without that constant looming dread of wasting irreplaceable fuel. But refueling is really just step one. Building on legacy concepts from things like the DARPA Phoenix program, companies like Redwire are using Archinaut technology to turn space into an actual workbench. Imagine a small satellite deploying into space and then robotically manufacturing and extruding its own 10-meter structural booms, or massive solar arrays, right there in the vacuum. And if we look a bit farther out, say to 2035, we're looking at modular satellite buses built with smart, self-healing materials. They're in early testing now, but we're talking about solar panels that can autonomously repair their own microfractures. It's straight out of sci-fi.
Which brings us to our final part, Section 5, the dual-use security dilemma.
Okay, so here's where this explainer takes a pretty serious turn. The inherent danger with all of this amazing tech is the dual-use nature of these Guardian satellites. Because at the end of the day, the exact same mechanics used for servicing are fundamentally the exact same mechanics used for co-orbital sabotage. Think about it. A highly precise robotic arm designed to carefully unscrew a fuel valve. Well, you could just as easily reprogram it to maliciously snip an adversary's communication antenna. Those giant space claws meant to drag dead debris into the atmosphere. They could theoretically grapple a fully functional national security satellite and force it into a destructive reentry. Even the advanced proximity LiDAR and machine vision needed to gently dock with a satellite allows it to covertly shadow and inspect an adversary's assets without them ever consenting to it. As the folks at Starburst Aero points out, even defensive measures can easily be perceived as offensive. It creates this profound geopolitical paranoia. Major spacefaring nations are now operating in a domain where true intentions are almost impossible to verify. If your servicing satellite approaches a friendly asset to give it some fuel, a rival nation watching on radar might legitimately perceive that as an incoming counterspace weapon maneuvering for an attack. And while the UN Committee on the Peaceful Uses of Outer Space is trying to propose norms for how to behave up there, the enforceability gaps are massive, simply because the technology itself is inherently ambiguous.
So I'll leave you with this to chew on. We are standing right on the edge of an unbelievable technological revolution that's going to make space totally sustainable and economically efficient. But as Earth's orbit transforms into this bustling, automated repair yard, how in the world do we regulate a domain where every single mechanic's wrench is also a potential weapon? How do we build trust in the dark? Definitely something to think about the next time you look up at the night sky. Thanks for joining me on this explainer, and keep questioning what's possible.